All right, picture this. You've got a complicated function, maybe something that's bouncing around sinus cosine's exponential growth. What if I told you there's a way to turn all that chaos into something much simpler? That's where the Laplace Transform steps in. The Laplace Transform is like a magic translator for math. It takes a function of time, usually something tricky to handle, and converts it into a function of a new variable, s. This new perspective turns calculus problems into algebra problems. Think solving a puzzle with fewer pieces. Let's talk properties. First, linearity. If I add or scale my functions before transforming, I get the same result as transforming them first, then adding or scaling after. Super handy when you're breaking apart complex signals. Second, shifting in time. If I delay my input function, it's like multiplying the transform by an exponential term. This is perfect for modeling situations when something kicks in after a certain point, like turning on a switch. Third, differentiation. The Laplace transform turns derivatives into multiplication by s. That means differential equations, which used to be the bane of my existence, suddenly become algebraic equations, much easier to solve. Initial value theorem, final value theorem. These let me peek at how a process starts or ends without actually solving the whole thing. It's kind of like skipping to the last page of a mystery novel, but for math. And finally, convolution. The Laplace transform turns the convolution of two functions into a simple multiplication, something that's incredibly useful for signal processing and systems engineering. So, next time you see a gnarly equation, remember, the Laplace transform is your toolbox for making math visual, intuitive, and honestly, a whole lot friendlier. Until next time, keep exploring.